Okay, welcome back. This is Mr. Hassan's Maths channel. I'm now answering question number 10, part B from the May-June 2022 Cambridge 9709 paper 3 variant 1. Question 10 part A was about differentiation and the product rule, and now we have got a question involving which is called iteration and numerical methods. And we're told to verify by calculation that A lies between 2 and 2.5. Just as a little reminder, in case you didn't watch the first part of the video, A is the value where the gradient of this graph is equal to 0. So when we solved this equation, we differentiated it, equated it to 0 for the stationary point, and then we basically replaced the x with A. We found that we ended up with an equation tan A equals negative A over 2, or tan A equals negative a half A, and the solution to that will be the value of A, which is the turning point. So if we want to now find the value of A by using iteration, okay, then we have to deal with this equation. Now, to prove that the root A lies between 2 and 2.5, what we do is, the first thing is you take the equation that you've formed and you make it equate it to 0. So you add half A on both sides, so it says equals 0, and then I'm going to write this as the function of A equals tan of A plus a half A. And now what I'm going to do is I'm going to replace the two values of A that they told us to use. I'll put A equals 2 inside this function, so we can say f2 is equal to tan of 2 plus a half times 2. And I'll put the other value, A equals 2.5. So I have f 2.5 equals the tan of 2.5 plus a half times 2.5. And I see what values we've got. Now, one thing that's really important for you to understand is that when we are dealing with calculus and trig functions, you must always deal in radians in your degrees, because one of the basis of the basic results is when you differentiate sine x, you get cosine x. Okay, and it's going to be exactly the same. Differential of sine x gives you cosine x. Now that will be exactly, the differential of sine x will be exactly the same as cosine x if and only if the angle is measured in radians. Okay, only if and only if the angle is measured in radians. If it's measured in degrees, then the differential of the sine of x will be some sort of constant times cosine of x. But in radians, they're exactly the same. And that's the basis for all the other types of differentiation in trig. So therefore, we must always use radians. Always use radians. So when you're doing a question like this, the angle here must be in radians. If this is the result of differentiation, the angle must be in radians. So we take the angle, we make sure, take our calculator, make sure it's in radian mode, and we put these values in. So I'm going to put tan of 2. Okay, tan of 2. What's going on here? All right, and then plus, it's going to be plus 1. That gives you a negative value, negative 1.185. Negative 1.185. All right, and then we put 2.5 in there. So I'll replace this by 2.5. So this is going to be a half of 2.5. I think that's 1.25. Whoops, what am I doing there? Sorry. So tan of 2.5 plus 1.25. Come on. That's better. Okay, that gives us a positive value, 0.5029. Continues. So we can see here that we have these two values. Now, what it shows us basically is that because there's a change in sign between these two values, between 2 and 2.5, the root must lie somewhere between them. Okay, and I'll just illustrate what I mean, just in case you don't quite get it. So supposing that is our x-axis, and this is the value A2, and this is the value 2.5. Now our root, to show that the root lies somewhere, A lies somewhere between 2 and 2.5, when we put 2 as a, we got here a negative value. Okay, when we put 2 as a in here, we got negative value. When we put 2.5 as a, we got a positive value. So we can see that somewhere between these 2 points, the curve must have crossed the x-axis. So a must be somewhere between them. Okay, so if I can show that the root lies somewhere between 2, if I can show that there's a change in sign between 2 and 2.5, that means the root must lie somewhere between 2 and 2.5. Somewhere between those two, the root occurred. So we can say as you can say f of a here is continuous, okay, between 2 and 2.5, between 2 and 2.5. Okay, and there is a change in sign. Now, this is the important kind of phrase they're looking for. There is a change in sign. Change in sign. So we can say a root must exist between a equals 2 and a equals 2.5. Okay, so that proves that there's a root somewhere between them. Okay, so there's part B. Now part C was actually the question that the student asked. That was the question that the student asked, right? And basically we have, this is our result for part A. So I think I'm going to need that down here. All right, so it says here that show that if a sequence of values in the interval between 0 and pi given by the iterative formula xn plus 1 equals pi minus inverse tan of half x converges, then it converges to a, the root of the equation in part A. So we're going to show that this iterative formula will end up giving us something that looks like that. Okay, so what we're going to do is we're going to take this equation here and we're going to put x equals pi minus the inverse tan of a half x. Okay, and we are going to replace the x with a. So you have a equals pi minus the inverse tan of a half a. And we're going to make this a the subject of the formula. I'm going to rearrange it and find what this a is. So what I'm going to do is I'm going to add inverse tan of a to both sides, of a half a to both sides. And this will leave me with, on this side, pi minus a. Okay, and now if I have the inverse tan of a half a equals pi minus a, then what I can say is that a half a, if I take the tan of both sides, a half a is going to equal the tan of pi minus a. Get rid of the inverse tan by taking the tan of both sides. All right, so now I have a half a equals tan of pi minus a. So we got to show or find what tan of pi minus a is. Okay, so now what I'm going to use is I'm going to use the compound angle formula for tan. Okay, which I'm going to get it from the formula sheet. Okay, so this is the from the formula sheet, the formula for the compound angle for tan. Okay, tan a plus b. So here we have tan theta minus a. So I'm going to consider the a to be my theta and the b to be my a in this formula. So I'm going to have the tangent of, you've got tan of a minus b, so I'm going to use the one that says plus at the top. So the tan of a, which is tan of pi, plus the tan of b, which is going to be the tan of a. Okay. In fact, I've got to use a minus here, sorry. The other way around. If that's a minus, that should be a minus. That's a minus, that should be a minus. So that should be tan of a, theta minus tan of a over, and then we have 1. And if that's a minus, that's a plus, plus the tan of a, which is the tan of theta, times the tan of a. Okay, now So I've just applied this formula. Now this is going to give me the tan of theta is 0. So I have 0 minus the tan of A over 1 plus, and the tan of theta is 0, 0 times the tan of A. So of course this part becomes 0. So we're left with that's equal to minus tan A, minus tan of A. All right, so now let's apply it to here. Let's replace now this with minus tan of A. So we just proved that this is equal to negative tan A. So you have a half A equals negative tan A. Okay, which basically is the same as this. If I just multiply both sides by minus 1, I've got the tan of A equals negative a half A, which is exactly what we had to show. I had to prove that it converges to the same root of the equation in part A, okay, which we found the equation of part A to be this. Right, so that's the answer to part C. Then it says part D, use the iterative formula given in part C to determine A correct to 2 decimal places. Give the result of each, in part C, sorry, give the result of each iteration to 4 decimal places. So we want to use this iterative formula to find the value or values, or to find the root of A correct to 2 decimal places. So we know that A is somewhere between 2 and 2.5. So we know that our A is somewhere between 2 and 2.5. All right. So what we can do is we can choose one of these values. For example, I can choose the first value of A to be 2. Now, how do I do this? I put this into the iterative formula. So I put A equals 2 into the iterative formula. So I can say A2 is going to be pi minus inverse tan of a half times 2. Okay, so I've replaced the A here with 2. Okay, so that's going to give me what? Let's see what that gives us. Again, remember we have to be in radian mode. So we have pi. So in this type of question, actually what you should do is you should take your value that you put in first and you type that value in your calculator, put 2, and I press equals, right? So to set this up properly, now that equals, when I press 2 and equals, that equals is now the answer in my calculator. So I'm going to set up the iterative formula, which looks like this, okay, such that I'll be able to use my calculator. So I'm going to do that now. So I'm going to take my iterative formula and set it up with the calculator with my initial value as 2. So when I press 2 equals, that's now the number in my calculator. So I put pi minus inverse tan of, and I'm going to put a half, 1 over 2, and then I'm going to put times answer. I'll close that bracket. So that's going to give me pi minus inverse tan of 2 first. Right, so when I press this, inverse tan of a half times 2, which is going to be pi minus inverse tan of, it's going to be a quarter. Right, that gives you 3/4 pi. In fact, 1, inverse tan of 1, which is going to be, inverse tan of 1 is pi over 4. So pi minus pi over 4 is 3/4. That gives you 3/4 pi. But they want to give each iteration to 4 decimal places. So I'm going to write this to 4 decimal places. I'll press SD. I'll put 2.3562. 2.3562, because there's a 9 here, that becomes a 2. 2.3562. So 2.3562. 4 decimal places. Each iteration to 4 decimal places. My final answer to 2 decimal places. So now my A2 value is going to be this value here, which is 2.3562. Therefore, my A3 value is going to be pi minus the inverse tan of a half times my A2 value. I'm not going to write it down, but it's basically this value over here. Now, the good thing about what I did is, because I put answer here, the next time I press equals, it's going to put this value in place of answer. Give me the exact same calculation, but instead of 2, it's going to put 2.356 or whatever. It's going to put this value in there in this exact form. So when I press equals, it's going to give you another iteration, which hopefully will get closer to the actual answer, like 2.2746. 2.2746, so 4 decimal places. And I just keep going until it settles down to one particular value. So I press equals again, 2.2920. 2.2920. So 2.29, was it 20? 20. Okay, and this now is A3. A4, sorry. That's A1, A2, A3, A4. I keep going until it settles down. So I just press equals again. That gives me 2.2883. 2.2883. That's the 5th iteration. Let's carry on. Okay, press equals again. 2.28907. 2.28907 or 91 to 4 decimal places. Now you can see it's starting to settle down. Okay, let's carry on a bit more to make sure, all right, that the next decimal place settles down as well. So I'm going to press equals again. 2.28889. A7, 2.28889, so 89. Right, so it looks like it's going to be 2.29. Okay, to 2 decimal places. So if I press equals again, you can see that it's going to settle there. Right, so that's enough for us to work out. So we're going to say that therefore the value of A, the real value of A, is 2.29. Okay, so that's the answer to A to 2 decimal places. All right, and if you wanted to prove that this is the answer to 2 decimal places, we can take the 2.29 and we can find the upper and lower bounds of this. So this is like 2.295 and 2.285. And we can put it back into the original equation, which was the one that we used here, okay, for tan A plus a half A. And we can see that there's a change in sign between these two values. If there's a change in sign between these two values, then somewhere between these two values, the root will be. And both of these values, when you round them, they're going to give you 2.29. And that's the highest and the lowest number can be rounded. That gives you 2.29. So you can prove that the root lies between those two. You can prove that that is the correct root to 2 decimal places. Okay, which is what they want in the end. All right, so we can just take that calculation. I think we made it before somewhere. Did we? Okay, let's do it again. So remember it was tan A plus a half A. Tan A plus a half A. So we're going to have the tangent of 2.295 plus a half times 2.295. Okay. Now that gives you a positive value. That's a positive value. Okay. And when you put in an 85 instead, all right, it should give us a negative value. Good. That gives us a negative value. So that's another way to prove it. Okay, what we've done here is sufficient. But if you want to show, sometimes it might say justify that the root lies, that this is the root to 2 decimal places, then we can justify it by finding, it's like you got your upper bound of 2.29, 2.295. You got the lower bound of 2.29, 2.285. Anything that's from there to there will round to 2.2923 SF. Okay, so, 2 decimal places if you want. So therefore, anything that, if the root is anywhere between these two values, it will round to this much. That's the lowest it can be, that's the highest it can be, such that it rounds to that much. So therefore, we can show, because there's a change in sign, the root must lie somewhere between these two. Somewhere between these 2 points, the line crossed. Okay, so there we have the answer to part D. Okay, so I think the main question here was part C, that some students might have been confused about. I hope that I've cleared that confusion, and that basically is the end of this question. As I said, part A of the question is on a separate video. You'll find that video as well as all the other videos that I've done from this paper in the playlist that will appear at the top right of the corner of this video, at the end of the video. You'll find other questions from the topic of iteration and numerical solutions. I'll put them over here. Okay, so that's collected by topic as well. You can subscribe to my channel by clicking on this link, and here you can find a video which explains how you can use my channel to find what you're looking for. Thank you for watching, and see you soon.